Hey everyone, a very warm welcome back to the channel. Today we are discussing the question number 8 from the chapter of Matrices and Determinants. The question is asking us, let A be the given matrix 1x by n minus x by n, comma 1. Then the value of limit of n tends to infinity of A power n is equal to how much? So the maximum time allotted for this question would be 11 minutes, and ideally you should try to do it within 4 minutes. So I hope you all have tried it out. Now the answer to this question would be cos x, sin x minus sin x, and cos x. So let's see some concepts and formulas used behind solving this problem. So characteristic polynomial of a 2 by 2 matrix A, we should know that it is equal to lambda square minus trace of A into lambda plus determinant of A. Characteristic equation and Cayley-Hamilton theorem, we should know. Basics of limits, addition, subtraction, multiplication algebra. We should know that of matrices, it behaves exactly like numbers if commutativity between them holds. So for example, if we have a matrix I and a square matrix M, they would always be commutative because Mi is equal to Im. Both of them are equal to M. Now let's see the method number 1. So method number 1 basically relies on forming the characteristic equation or polynomial of the matrix A. So obviously its trace is going to be 2, very easy to observe, and the determinant is going to be 1 plus x square by n square. Now it's easy. Now what we are doing is that we are going to go ahead with polynomial division. So we are dividing lambda power n by this p of lambda, and we are assuming that we are getting a quotient as q of lambda plus we are getting remainder as r of lambda. Obviously, since p is quadratic, it will remainder is going to be a linear function, so we have assumed it to be u lambda plus v, and that's what I have substituted in place of the remainder, and this we are calling as equation number 1. Now let us assume that alpha and beta are the roots of p of lambda. So if we put lambda equal to alpha, then beta in equation number 1, we are going to successively get these pairs of equations, which we are calling as equation number 2. Now, once we have done this, we can easily eliminate v. How are we going to do that? We'll just subtract the equations. So v and v cancel out, and u we are able to get as alpha power n minus beta power n upon alpha minus beta, which we are calling as equation number 3. Now on solving p of lambda equal to 0, we obviously get its roots alpha comma beta as these two roots 1 plus minus iota x by n. It's very easy to solve. Just use the quadratic formula directly. So without loss of generality, let alpha be this root and beta be the other root. It simply doesn't matter. You could have called this as alpha, this as beta, then also we'll get the same answer. So it really doesn't matter which one we call alpha, which one we call beta. This, of course, we are calling as equation number 4. Now, in equation 1, what we are going to do is, look, this is always true for any lambda where lambda is a real number, right? Or even a complex number, right? But it will also, we can also replace it by a and get this equation. The reason is the only matrices present in this relation are A and I, nothing else. And obviously they are commutative. So their algebra will behave exactly just like numbers. So that is why we have been able to replace it by A. Okay, so it is not always true. We cannot always do this. But since commutativity holds true here, so we could have done that. Now by the Cayley-Hamilton theorem, Cayley-Hamilton theorem basically guarantees that characteristic polynomial, whenever in that we replace the lambda by the matrix itself, by the matrix A itself, that will give us the null matrix. So basically we are saying that every matrix, every square matrix satisfies its characteristic equation. And what is the characteristic equation? P of lambda equal to 0. So obviously lambda can be replaced by the Cayley-Hamilton theorem. So we can say that since this is 0, a power n simply would become ua plus vi as it is, right? Now we just put in the values of a and I. So this is what we are able to obtain. Now, once we have got this, what we are doing is we are using equation number 2. So from equation number 2, I am able to put the value of v as alpha power n minus u alpha. Okay, so what we have done is everywhere the value of v we have replaced by alpha power n minus u alpha. Here also we have done the same, remaining no changes, remaining things remain as it is. Now of course alpha power n is there, alpha power n is there, u can be taken common between both these terms, that we have done. So u into 1 minus alpha. Now once we have got this, of course, now what we can also do is we can use the equation number 4, in which we have said that alpha is equal to this much, right? So 1 minus alpha value would be minus ux by n. So that's, or rather minus x by n. So it's very easy to observe that 1 minus alpha would be minus iota x by n. So that is what we have substituted. U was already there actually, so minus iota into x by n. So that is exactly what we have done here as well. Now this we are calling as equation number 5. Now it is very easy to observe that limit of alpha power n as n tends to infinity would simply become this quantity. Let me call this L. Taking logarithm, ln L, comes out to be this quantity. Now ln of 1 plus x can be replaced by x if x tends to 0, and obviously this is tending to 0 because anything upon infinity will tend to 0. So using that trick we are able to get here n and n get cancelled, so we are left with iota x. So obviously L comes out to be e power iota x because this was logarithm of L. Now that's why this limit is e power iota x, which we are calling as equation number 6. In exactly the same way, we could have also derived the value of this limit. It will come out to be beta power n e would be equal to e power minus iota x, which we are calling as equation number 7. Now from equations number 3 and 4, we can write this thing. How are we able to do this? Let me illustrate it more in more detail. So equation number 3 was this, right? U is equal to alpha power n minus beta power n upon alpha minus beta. But from equation number 4, we have the values themselves. What is alpha? What is beta? So alpha minus beta obviously comes out to be 2 iota x by n. So this value I am substituting in this equation number 3. So that's how we are getting this quantity, right? 2 iota x by n here. So obviously u into x by n would come out to be alpha power n minus beta power n upon 2 iota. So upon 2 iota is here. But since I have also applied the limit, so alpha power n limit would be replaced by e power iota x from this equation number 6. So that's how we are writing this e power iota x and then minus e power minus iota x. Obviously that this thing, entire thing simplifies to sine x. So this is the equation number 8 that we are getting. Now from all these equations of 5, 6, 7 and 8, look what we are doing. This equation number 5 we had, right? Just apply limit both the sides and tends to infinity. This limit would obviously become e power iota x. So that is what we have written here. This second limit u x by n would become sine x. So that is what we have done. And that is exactly what we have done for all the other terms. And once we get that and you simplify using e power I theta, we know it is equal to cos theta plus iota sine theta. This is the final answer that we get. Okay. Now let's see the method number 2. The method number 2 relies on basically splitting the matrix A in this manner. So this matrix plus the identity matrix. So basically what we are doing is this matrix we are calling as P, and obviously this is I. Okay, so A is equal to P plus I. Now what we can observe is that P square actually comes out to be this quantity, and this can obviously be written as minus x by n whole square into I. If you take this out common, it is easy to observe that we have written correctly. Now P cube, how will we find P cube? Just multiply both sides by P. So we get P cube is equal to minus x by n whole square into P. Then similarly, we can get P power 4 by multiplying by P again both the sides. So here it will be P square. P square value you again substitute from the first equation as minus x by n whole square into I. So this is the final value of P power 4. Then similarly multiplying by P again both the sides, P power 5, this we get. So it is very easy to observe the pattern that they are going to follow. So A power n would simply be P plus I whole power n. Now since P and I are commutative, we can directly apply the binomial theorem because algebra will behave just like numbers. So this is the expression that we are getting. Now what we are doing is we are clubbing them in a particular way. So all the even indexed terms, like where this 0, 2, 4, these are even, those I have combined together. Basically what we are doing is even powers of P we are clubbing together, and the odd powers we have clubbed together. Now of course P square was simply minus x by n whole square into I. Okay, so those values we keep on now putting here. Simply similarly P power 4 was x by n power 4 into I. So I has been taken out common here, right? And remaining things have been put as it is. Similarly P power 1 value is simply P power 1 only, but P cube is minus x by n whole square into P. So that also we have substituted in. So after doing that, P will come out common from this second bracket, right? and we have been simply able to, or in other words, we can also understand it like you first take out P common. You first take out P common. So P comes out common. What will be left inside? Again, the same terms. I will, here we will be remaining with I. Here we'll be, left with P square. Here it will be P power 4. So exactly these terms only we'll have to copy down, right? Because the terms are precisely the same. So once we have done that, the problem is pretty easy. We should also note that P can be written as this quantity by taking x by n common. So the thing is that what we have done is we have substituted in the values now. A power n is equal to I is simply this value which we have put here. These remain as it is, and I'm also substituting in the value of P here. So here it is 1 minus 1 1 0 1 minus 1 0, and the x by n has been sent inside the bracket for multiplication. Now you just apply the limit both the sides. We can easily observe this is what we would get for this bracket, and for the second bracket this is the expression that we are getting. Obviously these are the expansions of cos x and sin x, and final answer we still get as what we got earlier. Okay. Another way, by the way, of finding out these limits is using binomial theorem. So like 1 plus iota x power n plus 1 minus iota power x power n. Also we could have tried to do to get to these values of these brackets that we have written, involving the NC2, NC4, these binomial coefficients. So their binomial theorem also could have been used, and then the limit could have been found. Either way, we would get the same answer. So I really hope you all were able to follow through the explanation, understand what exactly we have tried to do, and both the methods were clear. So I hope this answered the question and you were able to understand. Make sure you like the video, comment down below what more you would like to see next, and share the video, subscribe to the channel, and I'll see you all in the next one.